Hey there, curious minds. Welcome back to the Deep Dive, your shortcut to becoming incredibly well informed on topics that matter. Today, we're taking a deep plunge into a topic that's quietly reshaping our world: machine learning. Not just as some cool technology, but thinking about it as a robust, reliable system. Something that actually lives and breathes in the real world. You might have dabbled in ML concepts, maybe heard about models and algorithms, but, well, our mission today is to unpack what it really takes to get ML to work dependably, beyond the lab, and why that's, frankly, more crucial than ever.
Yeah, and what's truly fascinating here, our source material for this deep dive is Reliable Machine Learning.
Yeah.
It's a book penned by experts with like decades of hard-won experience at places like Google, Amazon, Microsoft, real trenches stuff. It's really a pragmatic guide for anyone looking to not just build, but actually deploy and maintain these ML systems successfully.
Okay, so what does all this mean for you? Whether you're maybe prepping for a meeting, trying to catch up on the field, or maybe you're just insanely curious. We're going to cover everything from how these ML systems kind of loop in production to why troubleshooting them is surprisingly tricky, and importantly, how different teams can actually talk to each other effectively to keep these complex systems humming along. So let's maybe start at the beginning. Machine learning has really truly undergone a profound transformation. It's moved way beyond just its academic roots.
Exactly. What used to be, primarily the domain of researchers and data scientists, well, now it's equally the responsibility of a whole range of engineering roles.
Mhm.
We're talking ML engineers, SREs, site reliability engineers. And this signals a really fundamental shift in focus. It's not just about making models work anymore. It's about making sure they work reliably and actually meet the organization's real-world needs.
Right. And this isn't just about getting a model to predict something simple, is it? It's about building these entire systems, these structures that let organizations efficiently produce models, deliver them, harden them against failure, enable recovery when things go wrong, and continuously improve them out there in production.
And that shift brings up a really crucial point. Why this intense focus now on reliability? You see a lot of ML books promising ease or speed, maybe, but reliability often gets, well, undervalued. The book argues pretty strongly that looking at it through an SRE lens gives you a more holistic, sustainable framework, one that always keeps the customer experience front and center, which, frankly, current development practices don't always fully address.
So it's about making ML robust, dependable, not just cutting edge for its own sake. The book definitely believes in the hype, that ML is reshaping society, but it's grounded in this reality that these systems can be surprisingly, almost laughably unreliable if you don't manage them correctly. Something that often catches people off guard is this idea that ML applications are truly never done. Not like traditional software. They don't just start and stop neatly in one place.
That's a really common misconception. We often see data scientists kind of hoping they can collect data, train a model once, and boom, finished. But that almost never happens in practice. There's this concept of the ML loop or life cycle, which really shows this continuous nature. Whether a model performs well or maybe not so well, it typically involves constantly tweaking training pipelines, changing features, adding or removing data, sometimes even restructuring the model itself. That first model is really just the starting point.
Okay, let's quickly trace this essential ML lifecycle or loop then. How does it work? First, you've got data collection and analysis. Teams figure out what data they need, prioritize it.
Right, the foundation.
Then ML training pipelines. These are designed to process that raw data into actual models. And this isn't just some script you run once, right? It's a production system. It needs meticulous care.
Oh, absolutely. Automation, auditing, they're crucial. You want to avoid that nightmare scenario where, say, a model was built by an intern who left, and now nobody knows how to regenerate it or what went into it.
Exactly. Okay, so after the pipelines, next comes build and validate applications. This is integrating the model into customer-facing systems, logging user actions for feedback,
And get it out there.
followed by quality and performance evaluation. And this apparently requires surprisingly detailed work, just defining what working actually means, measuring performance, often using SLOs, service level objectives.
Yeah, defining good is harder than it looks.
And finally, release and updates. This involves careful progressive rollouts and making sure that feedback from how real users interact with it gets fed back into data collection for the next cycle.
Exactly. It's truly a continuous learning loop. It never really stops.
So if ML is this continuous loop, then data is truly at its heart, isn't it? This deep dive really emphasizes that the data used to build the models and the pipelines that transform it, they're absolutely paramount.
Indeed. And data in production, it has its own life cycle too. You've got ingestion, cleaning, and ensuring consistency, enrichment and extension, storage and replication, actually using it in training, and finally, deletion, maintaining stable data definitions, metadata definitions, plus robust version control. It's all crucial.
But data isn't just an asset, right? It can also be a pretty significant liability. Privacy concerns loom large here.
Absolutely. The book really hammers this home. Minimizing the privacy attack surface is crucial right from the very start. This means things like data minimization, only collecting what you absolutely need, and data separation, keeping sensitive stuff like names or addresses clearly separate from the core model data, like click predictions. Plus, you need strict data access guidelines. No personal use, no looking up acquaintances, basically no analyses you wouldn't want made public.
And encryption is a major strategy too, I imagine.
Definitely. With the big caveat that you need extremely reliable key handling systems. You don't want to encrypt everything and then lose the key.
Yeah, that would be bad. Something that's often overlooked is just how sensitive these ML pipelines are to their input data, way more than most other data processing pipelines.
It's a critical difference, yeah. They can be incredibly sensitive to even subtle shifts in the data distribution. A small, maybe seemingly insignificant, non-random omission or change. It can cause a pipeline to go from mostly right to significantly wrong.
Wow.
And that sensitivity makes aggregating, processing, and continuously monitoring the data itself, not just the live systems, absolutely critical. For example, slicing data along different axes, like maybe how old the data is,
Yeah.
can give you really key monitoring insights into potential problems or drifts.
The book also gets into data categories structured, unstructured, semi-structured, and how their internal makeup affects processing.
Right, which also leads into the whole question of bias.
Yeah, how do we address bias in our models? It's not just bad data, right? It can be bad modeling choices too.
Yeah, exactly. Bias can come from how you sample data, historical biases already present in the data, or even implicit social biases baked into how things were recorded. The circumstances of data creation have really profound implications for correctness, fairness, ethics. Having processes like model cards is critical here. And honestly, having a diverse, inclusive company culture with different perspectives, that can be a really robust defense against embedding unintended bias.
So data management isn't just about storing files. It's quality, integrity, ethics, the whole life cycle.
Yeah.
Okay, so we've carefully gathered and managed our data. Now let's talk about the models themselves. When we say model in ML, we're definitely not talking about a neat little equation like EMC squared.
Right, not at all. ML models come into play where human experts just can't specify all the rules because the information is too complex. Think of thousands of atmospheric readings or incredibly long purchase histories. You can't write rules for all that. So we turn to vast amounts of previously observed data to train these models. The hope is they learn patterns from the past and then predict well on new data they haven't seen before.
And for supervised ML, you need that label, right? The historical outcome you want to predict.
Exactly. Like, did it rain yesterday? That's a 1 or not? That's a 0. Yeah. Or what was the exact sales count for this product last week? That's your label.
Okay. And there are different kinds of models.
Oh, yeah, a whole zoo. From deep learning, which uses these complex neural networks and really thrives on massive data sets, to things like random forests, which can be very effective even with less data. There are even tools like AutoML that try to help pick the best model type for your specific problem. And then you have hyperparameters. Think of those as the knobs or settings you adjust before the model starts learning, guiding the overall training process. They need careful tuning.
Right. And after validation, the models get deployed, either pre-computing predictions or serving them live.
Correct. Pre-computing everything offline or serving predictions on demand as requests come in.
Okay, this is where it gets really interesting for me. Where are the hidden vulnerabilities? Where do these models tend to break down in the real world?
Many places. The data itself is a huge source. For training data, you've got issues like cold start, like no history for a brand new product. How do you recommend it? Or incomplete coverage, maybe. Your model predicts worldwide purchases, but was only trained on US and Canadian data. That's a problem. And spurious correlations, where the model learns some irrelevant pattern that just happened to be in the training data, but doesn't hold true generally.
Okay, what about the labels?
Yeah, labels. If those historical outcomes are inconsistent, or if they reflect existing societal biases, maybe historical hiring data reflects past discriminatory practices, the model will learn those biases directly.
Oof. Okay, what about the training methods themselves?
Well, with training methods, take deep learning. It relies heavily on randomization internally, which means even if you train the exact same model on the exact same data twice, you might get slightly different results, which can be confusing. It's also notoriously hard to know when training is really done. You risk overfitting where it learns the training data too well and fails on new data, or this weird double-dip phenomena. Plus, deep learning is super resource-intensive, computationally expensive, and it can sometimes make these really extreme, very wrong predictions when it encounters data that's totally unfamiliar to it.
Wow. Okay, what else? Feature generation.
Yes, feature generation errors. This is subtle, but critical. It happens when the features, the inputs to the model are calculated differently during the training phase versus when the model is live serving predictions. Maybe a slight difference in how you handle missing values or normalize a number. These can lead to prediction errors that are incredibly hard to detect later.
Okay, and finally, upgrades and fixes. This sounds counterintuitive.
It really does. But think about upgrades and fixes upstream. Maybe there's a bug fix in a data source, like a temperature sensor gets updated and suddenly starts reporting in Celsius instead of Fahrenheit. But nobody tells the ML team. If the model was trained expecting Fahrenheit, its predictions will suddenly go completely haywire. It's what the book brilliantly calls better is not better, better is different. The change was an improvement, but it broke the downstream model.
That better is different idea is so critical. Wow. Okay, so it seems we also need to be clear about terminology. There's the model architecture.
Right, that's the general strategy. Like, are we using a deep neural network, a random forest? What's the overall approach?
Then the model definition or configured model.
Yeah, that's the specific configuration plus all the context needed to reproduce it. The training environment, the exact features used, the hyperparameters, even the random seeds for things like deep learning.
And finally, the trained model itself.
Exactly. That's a specific instance of a configured model trained on a particular snapshot of data at a specific point in time. It's the concrete artifact.
Okay, and if we connect this to the bigger picture, feedback loops, models influencing their own future data.
Yes, this is a huge one. Many models operate within feedback loops. Think about recommendation systems. They filter what users see or recommend certain items. The user's interaction with those recommendations then creates or influences the data used to train the next version of the model.
Ah, so it can lead to self-fulfilling prophecies.
Precisely. Or ML echo chambers. If the model only shows you stuff it thinks you'll like and never shows you anything else, then data that was initially selected never gets positive feedback, reinforcing the model's initial bias. You often need intentional exploration, deliberately showing lower range or diverse items to counteract this drift.
Okay, so building the model is one thing. Knowing if it's actually working is another. MLOps folks really crave validation, right? It's core to preventing system failures.
You're absolutely right. First, there's model validity. Does it even load in production? Does it crash the infrastructure? Is its computational performance okay? Like, for real-time translation, you need super tight latency. Can it meet that? Gradually increasing traffic using canary levels in production is a standard best practice here, just to make sure it doesn't break things.
But validity is just, does it run? That's not the whole story. How do we evaluate actual model quality? Is it any good?
Right. For that, we rely heavily on offline evaluations, often using a combination of a metric and a distribution. So if someone says, hey, this new model has better accuracy, the immediate follow-up question has to be, okay, better accuracy on what distribution of data?
Ah, right, because if you only test it on easy, perfectly clean data.
Exactly. If you use purely IID independently and identically distributed test data, which is like perfectly random representative data, it can sometimes give you an unrealistically optimistic view, especially with time series data like stock prices. You have to be careful the model isn't accidentally seeing the future in the test set.
So you need careful reasoning, common sense. Okay, this brings up an important question. How can we dig deeper? Go beyond basic metrics to really understand performance?
Great question. Two key techniques are sliced analysis and counterfactual testing. Sliced analysis means filtering your evaluation data by specific feature values. Like, how does our image recognition model perform specifically on images with snowy backgrounds, or for users in a particular country?
Okay, looking at subgroups.
Yeah.
And counterfactuals.
And counterfactual testing involves asking, what if? What would the model predict if the input data were slightly different? For instance, what if we change the background of this dog picture? Does the prediction change? Or, for a credit application model, what if we change the applicant's city? This often means creating synthetic examples just to probe the model's sensitivity and logic.
Gotcha. So what are some of the key metrics people use to assess this quality?
Well, there are several important ones. Bias. This is the difference between the predicted value and the correct value. We usually want this to average out to 0. But Zero bias alone doesn't guarantee a good model. It's more like a great canary. If it's way off zero, something's definitely wrong.
Okay.
Calibration. This is crucial for models that predict probabilities, like the chance a user clicks an ad. Calibration plots help you see if the model is systematically over or under predicting probabilities across different ranges. Accuracy. The simplest one, just the fraction of correct predictions, but context is absolutely everything here. 99% accuracy sounds great, but it could be terrible for predicting if it's safe to cross the street. Meanwhile, 0.1% accuracy might be amazing for predicting lottery numbers.
Right.
Always ask, what's the base rate? Like, if 99% of emails are not spam, a model that just predicts not spam every time has 99% accuracy, but is useless.
Good point. And 100% accuracy.
Often signals a problem, usually overfitting, or maybe the label somehow leaked into the input features.
Okay, what else? AUC, ROC.
AUC, ROC area. Under the receiver operating characteristics curve. It sounds complicated, but it's a really useful threshold-independent measure of quality for classification models. Great for comparing different models fairly.
And precision recall.
Precision recall curves. These show the trade-off. At different decision thresholds, how does precision, how many of the things I flagged are actually relevant? Trade-off against recall. How many of all the relevant things did I manage to find?
Makes sense. And error metric.
Right, like mean squared error, MSE, and mean absolute error, MAE. These are good for regression problems, where you're predicting a number and want to measure how far off your predictions are from the actual ground truth. Useful when errors can be positive or negative.
This whole discussion, especially around bias and metrics, naturally leads us straight into some critical ethical concerns. The book really emphasizes fairness, privacy, responsible AI. They're presented as paramount.
You've hit on a core truth, absolutely. That phrase, garbage in, garbage out, isn't just about technically bad data. It's also about outcomes stemming from unrepresentative training data or algorithmic choices that introduce or amplify bias. Bias can creep in from sampling methods, historical biases already baked into the data itself, or even implicit social biases held by the teams building the systems.
So when we talk about fairness in ML, it feels complex. Is there one single definition everyone agrees on? Or does it shift depending on the situation?
That's a really crucial point.
Yeah.
No, there isn't a single universally accepted definition of fairness. Different mathematical definitions exist, and sometimes they even conflict with each other in practice. You literally can't satisfy all of them simultaneously. The field is still maturing, and honestly, convergence on one definition isn't really the goal right now. Instead, the focus is more on making practical progress using the available definitions, while being really conscious that the people developing these systems often come from dominant groups and might therefore inadvertently miss negative impacts on underrepresented communities if they're not careful.
So it's about consciously baking in normative values, making deliberate choices about what's morally or socially desirable right into the ML design process.
Yes, precisely. And this means considering different strategies for intervention when unfairness is detected. There's pre-processing, trying to modify the data before training to remove bias. In processing, modifying the learning algorithm during training to promote fairness. And post-processing, adjusting the model's outputs after training to correct for bias.
And each has pros and cons.
Exactly. Each has trade-offs in terms of accuracy, complexity, and what kinds of fairness they can address. There's no single silver bullet. And sometimes, algorithmic fallbacks are necessary. Things like temporary non-algorithmic solutions, routing edge cases to human review, or just being radically transparent about the model's limitations when its performance is problematic.
It really sounds like this is a continuous journey, not a destination you just arrive at. The world changes, models drift, our understanding of fairness evolves. Plus, you have significant legal implications around discrimination to worry about.
Absolutely. And linking back to privacy, minimizing that privacy attack surface is critical throughout. Practices like data minimization, only collecting what you truly need, and data separation, keeping sensitive identifiers away from the model's training data are key. And strict data access guidelines are non-negotiable. No using data for personal reasons, no looking up people, basically operating as if every analysis could become public.
Okay, and finally, this umbrella term, responsible AI.
Right, it captures many of these ethical concerns. A key pillar within it is explainability, which is all about analyzing and presenting information to describe how an ML system actually works, why it makes the predictions it does.
But there's no single right explanation.
Exactly. It needs to be tailored to the audience and the purpose. What does a regulator need versus what an end user needs versus what a developer needs? They're different. But at a minimum, End users should generally have some idea of the inputs considered and maybe the relative importance of different features. Generating those counterfactual examples we talked about, like showing how a credit decision might change if gender was different, can provide really intuitive explanations.
Okay, and another core concept mentioned is efficacy. What's that about?
Efficacy means the algorithm must actually produce its desired or intended result reliably. Its logic needs to be externally valid. It should generalize effectively to the real world, not just work on the test data. We've seen those worrying examples where, say, a hiring algorithm doesn't actually predict who would be a good hire, but maybe just predicts who is unlikely to get hired based on past patterns, which can lead to self-fulfilling prophecies, reinforcing existing biases rather than finding good candidates.
So applying responsible AI principles needs to happen throughout the entire pipeline.
Essential. From the very beginning, brainstorming use cases, thinking about privacy, human dignity, the stakes of the decisions, all the way through data collection, modeling, quality checks, and deployment. It has to be woven in.
Okay, so once we have confidence in our models, our ethical approach, we actually need to train and serve them. What does a well-designed ML training system look like?
Yeah, a robust training system typically have a few key parts. You need a model management system. This tracks metadata, like the configuration, hyperparameters used, who built it, and keeps snapshots of trained models. Those snapshots are vital for things like transfer learning or just disaster recovery.
Okay.
Then orchestration, something to coordinate and track all the moving parts of the training system, schedule the jobs. This is where specialized tools like Apache Airflow really shine, more so than general orchestrators like Kubernetes.
And monitoring.
And robust monitoring, absolutely. And interestingly, the book argues that tracking training system throughput, how quickly can we reliably train and retrain models, is probably the single most important metric for the health of the training system itself.
It sounds like an inherently messy process, though, doesn't it, training these things?
Oh, it definitely can be. There are lots of common problems you run into. First off, models must be retrained. We've said it before, but they are never done. The world changes constantly, new data comes in, maybe your software tools get updated, and you need to verify things still work. Data will be unavailable. Distributed storage is great, but it has failure modes beyond just losing data. Sometimes data just becomes temporarily unreachable, stalling your training. Features will be added and changed. This is a huge part of ongoing model development, which often leads to needing dedicated feature stores to manage them consistently.
Okay, and models training too fast. How is that a problem?
Yeah, it sounds weird. But imagine you're fine-tuning a really complex machine. Instead of making small, careful adjustments, you get this flood of instructions all at once, maybe even contradictory ones. That's kind of what happens in distributed ML training sometimes. Updates from different workers can pile up or arrive out of order. Instead of the model converging towards the right answer, it can actually diverge and start producing garbage results.
Wow, okay. Resource use.
Resource utilization matters, big time. ML training is incredibly computationally expensive. So, efficiency is key. You need to measure the value produced divided by the cost. Using money-indexed cost is real, but it can be misleading if hardware prices change. Compute-indexed cost often gives a better signal for actual system improvements.
And data issues again.
Always. Data sensitivity and lack of representativeness. This is such a common source of unexpected behavior or bias, like that Yarnit example. They accidentally excluded all discounted purchases from training. So the models just stopped recommending discounted products even though users were still buying them. A simple data exclusion had a huge business impact.
And reproducibility.
Yeah, reproducibility issues. Especially with deep learning's randomization, training the exact same model on the exact same data might still give slightly different results. Periodically retraining models completely from scratch is expensive. But only doing incremental updates can lead to models drifting away from current reality. Maybe they still haven't forgotten fraudulent transactions that were later identified and removed from the source data.
Okay, so that's training. What about actually serving these models to users, getting the predictions out there?
Right, serving. The first things you absolutely need to understand are load, how many queries per second, QPS, will you get, and latency. How quickly does the model have to return a result? Solving for these often involves replicating the model across multiple servers, using powerful hardware like GPUs, which are fantastic for the dense matrix math common in ML, but they are specialized.
Yeah.
Or sometimes simplifying the model itself to make it faster.
And latency isn't just about the average.
Critically important point. Don't just look at average latency. Look at the percentiles, especially the high ones like the 99th percentile, P99. Your average might look great, but if 1% of your users are getting really slow responses, that's a significant negative customer experience you're missing.
Okay, so where do these models physically live when they're serving?
Good question. Options really boil down to the cloud, on local machines, like servers you own, or right on device. Think mobile phones, smartwatches, maybe even cars. On-device serving, often called serving at the edge, has really strict constraints on model size and power consumption.
And how are they practically managed for serving? Stored, loaded, version updated?
For online serving where speed matters, models usually need to be loaded into RAM for fast access. And you need mechanisms to continuously swap out old versions for new ones without downtime. And often, the feature pipeline for serving the part that takes raw input data in real time and transforms into the features the model expects is actually the most production-critical piece and a major source of latency, more so than the model inference itself sometimes.
Interesting. So what are the main architectural choices for how you actually serve them?
Broadly, two main patterns. There's offline serving. This means you pre-compute all possible predictions ahead of time and store them in a fast cache. When a request comes in, you just do a quick lookup. It's generally simpler and offers potentially better performance if you can predict the inputs.
Okay. And the alternative?
Online serving, often called Model as a Service, MOS. Here, the model runs live, takes streaming data as input, and generates predictions in real time. MOS gives you good separation of concerns. The model service is distinct from the application using it and isolates deployments.
And you mentioned serving at the edge, too.
Right, that's the third important architecture, specifically for running models directly on user devices.
And designing the API they interface to these models must be crucial for making them usable.
Absolutely crucial. ML models get built using a huge variety of languages and frameworks. Having abstracted web service APIs like standard RESTful APIs makes them much more accessible and allows different systems and teams to interact with them easily. And your key performance indicators, KPIs for serving, need to cover both model performance metrics, is it accurate, and system-level metrics like API latencies and error rates.
And scaling these up presumably means things like running clusters in multiple data centers for high availability and backup strategies.
Exactly. Standard high availability practices apply. Redundancy, geographic distribution, robust backup and recovery for your current model data and configurations.
And when we think about ethics and fairness in the serving context.
Yeah, organizations really need to establish checks and balances here, be transparent about how data is being used by the model, and critically minimize that privacy attack surface during serving too. Avoid logging personal information if possible, maybe use short-lived user identifiers that expire quickly.
Okay, so with all this complexity in training and serving, things are inevitably going to go wrong sometimes, but incident response in ML sounds like it's often very different from dealing with traditional software outages. Why is that?
That's a really critical distinction, yeah. Troubleshooting ML incidents can pull in many more parts of the organization, way beyond just engineering. You might need finance involved, PR, legal, especially if there are ethical or fairness implications. And the privacy aspect is huge. You can't just say, let's get the system working first, we'll worry about data privacy later. That's not acceptable. Privacy has to be considered during the incident response.
So what are the basics of managing an incident in this unique ML context?
Well, the fundamentals are similar to general incident management. You need to know the incident state, establish clear roles, incident commander, comms lead, ops lead, ascribe to document everything, subject matter experts. And recording information meticulously for follow-up and learning is crucial. The phases are generally detection, remediation, resolution, and then follow-up or post-mortem.
But what makes ML incidents specifically unique? What are the common failure modes?
Okay, so ML systems very commonly fail because of problems with data and metadata. That's probably the #1 cause. The metrics for success are also more complex. You're balancing pure model quality metrics against the actual business impact, which might not align perfectly. And failures can be really subtle. They might not trigger obvious system alerts. Sometimes the first detection comes from end users noticing weird behavior.
Like the Yarnet examples.
Exactly. Those Yarnet stories are perfect illustrations. Remember the one where a data team changed a unique partner ID key? That meant new log data couldn't be merged with historical data for that partner. So the ML recommendation model effectively stopped seeing any sales from that partner for 2 weeks, and it stopped recommending their products.
Resulting in a 40% sales drop for the partner. Wow.
Right. And the detection wasn't a system alert, it was the partner calling up and complaining. It really highlights the need for end-to-end quality metrics that actually track business outcomes, not just internal system health.
Okay, and the other Yarnet case, with the weather and stock issues.
Yeah, that one involved external factors.
Right.
Weather, changing customer preferences, people wanted cotton, not wool, combined with a supplier issue leading to inventory shortfalls.
Yeah.
The recommendation model first started showing weird recommendations, then just fewer recommendations overall. Why? Because it was learning customers weren't buying products that the store didn't actually have in stock.
So it wasn't really an ML model failure in that case.
Exactly. It was accurately reflecting a real-world supply problem. And sometimes the fix isn't in the ML system itself. The mitigation had to come from outside, like the business, deciding to offer notifications for when out-of-stock items return. The model was doing its job. The context around it had changed.
These stories really drive home the unique challenges. Okay, so what principles should guide ML incident management given all this?
Preparation is absolutely key. You need to organize and version everything, meticulously models, data, the code that transforms data, preferably in something like a feature store. Store historical versions of your trained models in a ready-to-serve format so you can roll back quickly if a new model causes problems. That's a crucial mitigation strategy.
Like a safety net.
Exactly. And specify an acceptable fallback plan in advance. What happens if the personalization model fails completely? Maybe you just fall back to recommending the overall most popular products.
Yeah.
And regularly test these fallbacks. Don't just assume they'll work. Also, decide ahead of time on useful model quality and performance metrics that are actually independent of the specific model implementation. Metrics that reflect the user experience or business goal.
And the roles involved.
Like the roles. It's a team sport. Model developers, product managers, data scientists, software engineers building the surrounding systems, and dedicated ML SREs or production engineers. They all have critical responsibilities, from ensuring data quality up front to building resilient software to implementing effective monitoring and alerting.
This raises a really important point about the on-call engineer during an incident, especially with sensitive data flying around. What are their ethical responsibilities?
This is absolutely core to what the book calls privacy-preserving incident management. The on-call engineer, even under the immense stress of an incident, needs to take extra care to respect user privacy. They need to be empowered to identify potentially unfair system behavior and prevent unethical uses of ML.
That sounds like a heavy burden during a crisis.
But it is. They need to consider the implications of their actions, perhaps consult with diverse colleagues if unsure. Often, the root causes of unfairness aren't malicious, but stem from homogeneous teams not considering all perspectives, or design decisions made early on without explicit ethical review. Solutions involve building diverse teams from the start, applying those responsible AI practices proactively and critically, restricting default access to sensitive customer data. Access should require justification, logging, and ideally multi-person oversight, even during incidents.
Okay, so we've covered the tech, the data, the models, the ethics, the incidents, phew. But how do you actually integrate all this into a real organization? You mentioned earlier, is Agile ML even really possible given these long feedback loops and complexities?
Yeah, applying traditional Agile methodologies directly to ML systems is, well, it's far from straightforward.
Yeah.
Like you said, feedback loops can be incredibly long months, sometimes even years before you see the real impact. It's not the quick customer feedback loop Agile thrives on. Integration involves people from all across the company, not just small, self-contained teams. Model development itself can have unpredictable delays. And as we keep saying, models are neither perfectly reproducible nor stable. They're genuinely never done. It breaks a lot of Agile assumptions.
The book outlines specific ML product development phases, though, right? Starting with discovery and definition. Why is that phase extra critical for ML?
Because it's where you have to tackle the inherent uncertainty head-on early. This phase is about clearly defining the problem you're trying to solve. Understanding the core business goal. Is it increasing sales, improving profit margins, reducing churn, and making a realistic assessment. Is ML actually a good fit here? If you need 100% accuracy, for example, maybe ML isn't the right tool.
And identifying risks.
Absolutely. Crucially, identifying the consequences of getting a prediction wrong. What happens if we recommend the wrong product? What if we wrongly flag a transaction as fraud? And defining safety nets based on that. Both intrinsic safety nets built into the system, like you physically can't cancel an order that doesn't exist, and extrinsic ones, like asking a user to confirm an unusual action.
And defining success metrics.
Yes, defining important business metrics up front, like for building a recommendation system, maybe click-through rate, CTR, is a key metric we need to track.
Okay, then after discovery, there's the model and product development phase, which needs intense collaboration, followed by deployment, and then that ongoing support and maintenance.
And that never-finished aspect really comes into play in support and maintenance. It's continuous. ML models require constant upkeep as the world changes, customer behavior shifts, business goals evolve. It's often really hard to draw a clean line between what's maintenance and what's new development. It all blends together.
So what about the classic build versus buy decision? How does that apply in the ML world?
It's nuanced. For the models themselves, generally, they must come from learning on your own specific data to be effective for your unique business context. You usually can't just buy a perfect off-the-shelf model.
But maybe for generic tasks.
Exactly. For very generic use cases like basic object recognition in images or standard sentiment analysis of text, pre-trained models can definitely be bought or licensed. That can save a lot of effort.
Okay, what about the infrastructure, the data processing pipelines?
For data processing infrastructure, the decision often hinges on your organization's existing technical skills and your tolerance for vendor lock-in if you go with a specific cloud provider's platform.
And end-to-end platforms, do those exist?
For end-to-end platforms that seamlessly cover everything from data prep to training to serving and monitoring, honestly, the book suggests there's currently no single, fully integrated solution that does it all perfectly. So decisions there really depend on your organization's overall data strategy and which pieces you prioritize building versus buying.
Let's make this more concrete. Looking at a web store, like the Yarnet example, how can ML specifically help?
Oh, in many ways. ML can significantly increase revenue and customer loyalty through personalized product recommendations. It leverages all sorts of data. The product catalog, user search queries, their viewing history, past purchase history, to suggest things they're likely to buy.
Beyond recommendations.
Yes, ML can also play a huge role in inventory management. By modeling complex supply chain constraints, predicting demand more accurately, it can propose optimal reordering strategies to minimize stockouts and overstocking.
But it sounds like making the necessary organizational changes to support ML can be really challenging.
It's a cliche, maybe, but it's profoundly true in ML because ML is so tightly coupled with data, and data exists everywhere in an organization. ML implementation inevitably touches almost every department. So you can't treat it as some mysterious, isolated tech thing happening over in a corner. Leaders need a holistic view and the ability to influence across traditional silos.
Which brings us back to that crucial point. Why do ML practitioners, more than maybe average product developers, need this broader awareness of business-level concerns?
Let's revisit those two powerful examples in the book because they really illustrate it well. Remember example 1, the cashmere yarn. The ML model was optimizing purely for sales volume. It started recommending high-margin cashmere like crazy because people bought it. But it didn't understand profit margins or, crucially, inventory levels, so they sold out of cashmere quickly. The unintended consequence. Customers who came for cashmere but couldn't get it might then abandon their entire shopping cart, meaning lost sales on other products too. The model succeeded on its narrow metric, but actually hurt the overall business goal.
Right. The local optimization hurt the global picture. And the second example.
Example 2, the user agent string. A web design team, maybe focused on analytics, starts logging the full browser user agent string for every visitor. Seems harmless, right? But they might be completely unaware that, especially when combined with other data like rough location, that string can become a unique identifier for individuals. If downstream ML models then start using this data without realizing its identifying power, the company could suddenly find itself violating its own privacy policies or regulations like GDPR.
Wow. A serious risk triggered by a decision made completely outside the ML team just because the ML team wasn't aware of the broader data context and business rules.
Exactly. It highlights this absolute need for a mindset of nuance and really strong cross-organizational communication and collaboration.
So how do you structure an organization for this?
Well, you can apply established organizational design models. The book mentions the Galbraith STAR model as one framework. It looks at the interplay between strategy, structure, processes, rewards, and people. The key is you don't have to change everything at once. You can sequence the changes. Practically, this might mean deciding between centralized ML teams, decentralized teams embedded in business units, or some hybrid model. Each structure has different implications for who you hire, people, how they work together, processes, and how success is measured and rewarded.
Right.
So the ultimate takeaway here is really about prioritizing that organizational change, hiring people who get the nuance.
And being patient.
Yes, prioritize the org change, hire for nuance and cross-functional thinking, and explicitly acknowledge that this transformation will take time. Regular, clear communication across teams is vital. The goal shouldn't just be to do ML because it's cool. The goal has to be using ML to genuinely move the needle for the business in a sustainable and responsible way.
And that really wraps up our deep dive into reliable machine learning. Wow. We've explored that huge shift from academic curiosity to a serious engineering discipline. We've looked at the absolutely critical role of data, the intricate, sometimes fragile nature of the models themselves, the non-negotiable ethical imperative around fairness and privacy, and those really complex organizational challenges of making ML truly work in the real world.
Yeah, and if you connect all those dots, if you look at the bigger picture, it becomes incredibly clear that reliable ML isn't just about having the fanciest algorithms. It's fundamentally about robust engineering practices, meticulous data management, proactive ethical foresight, and deep strategic organizational alignment. It's a whole package.
You've hopefully gained an essential understanding today of why these ML systems are never really done, and why their reliability hinges just as much on the people and the processes surrounding them as it does on the actual code. So for you, the learner, thinking about all this, it raises a really important question, I think. Given that even seemingly small errors or miscommunications in data handling, like that partner ID change, can cascade into significant model failures with real business impact, how might an organization best cultivate a culture where that crucial inter-team communication about data, about changes, about context, how does that become not just encouraged, but truly ingrained in daily operations, almost second nature? What does that actually look like in practice?